Okay, let's continue with elementary examples of normal spaces which you have probably seen before. Example 3 will be denoted capital C square brackets A comma B. This is the continuous functions f from the closed bounded interval AB to the real numbers C of the interval AB. I have to give it a norm. We'll give it the sup norm. So the norm of a function f is the integral from A to B. I'm sorry, it's not. It's the supremum of the absolute value of f of x such that x is in the closed interval AB. That's the sup norm for functions. Notice that in this case I could have called this the maximum by continuity. The so-called extreme value theorem from calculus and compactness of the interval AB. Compactness of the closed bounded interval AB. You learned in calculus that on a closed bounded interval, every real valued function attains both its maximum and minimum, in particular the absolute value, has a maximum which will then be the supremum of the absolute values. This is a norm space, and it's complete. It's a Banach space. To see why, let me remind you of another type of convergence for functions. To keep the number 3 because we're still talking about example 3 here. Remember that for functions we can talk about uniform convergence. You say that a sequence of functions S of n converges to f uniformly on the closed interval AB to mean that for all epsilon greater than 0, there exists an n sub 0 in the natural numbers such that the absolute value of f sub n of x minus f of x is less than epsilon for all n greater than or equal to n sub 0 and for all x in the interval AB. In your first analysis course beyond calculus, you probably talked about uniform convergence of functions. And one of the theorems you saw was that every uniform limit of continuous functions is continuous. And that's the underlying reason why C brackets A comma B is a Banach space.